Hello and welcome to MakeLearn 360. In this video, I explain to you how to look at the relationship between a force in space and individual components. So what I want to do is that I have a force F with component Fx along the x, Fy along the y, Fz along the z. So I want to look at the relationship between the force F and then its individual components. So what I will do is that I will draw a cuboid, and this cuboid has length Fx along the x, Fy along the y, and Fz along the z. Now what I want to do is to place this, so let's look at it. Considering the diagonal OA of the box along which the force F is acting. So look at this diagonal OA and this F. So what we can say that, okay, with respect to the the x direction, I have this force and then the x direction. So look at Fx. I have theta x here. Now to look at it carefully, I'll cut a plane containing the force and then the x direction. Alright. So let's look at this carefully. Now I can say that clearly for this triangle, cos theta x is going to be adjacent on hypotenuse, which is Fx on F. And so Fx is going to be F cos theta s. Now I'll go back and do the same for the y direction to cut it again. Now you can see that, okay, so cos theta y is going to be Fy on, Fy on F. That is to say, so that's what I was trying to say. For triangle OAE, I have cos theta y to be Fy on F. And so Fy is going to be F cos theta y. Alright. And so I'll go back and do the same for the z direction and cut it again. Now finally for triangle OAB, I can clearly say that, I can clearly say that for this triangle, I have cos theta z to be Fz over F. And so Fz is F cos theta z. Alright. So what I have done is that I've been able to look at the relationship between the force F and then the component along the x, y, z. So from these relationships, I can say that Fx is F cos theta x, Fy is F cos theta y, and then Fz is F cos theta z. Now the three angles theta, so theta x, theta y, theta z, define the direction, okay? And so the cosine of these angles is rather what we are calling the direction cosines. Alright. And so direction cosine is nothing but cos theta x, cos theta y, and cos theta z. So using the unit vector approach, I can resolve this into the I, j, and the k components. Now let's look at something interesting here. Since this is f, this is also f, this is also f, I can factorize f out so that I get cos theta I plus cos theta y plus cos theta z. Now you are multiplying f by something and getting back f. It means that the magnitude of whatever is here should be 1. And which vector has a magnitude to be 1? That must be a unit vector. And so I can multiply this force f when I know the scalar by a unit vector in the direction of the force. Now clearly speaking, the unit vectors can also be represented by lambda x, lambda y, and lambda z, meaning that the unit vectors themselves represent the direction cosines. Now very important, look at this relationship here. Cos squared theta s plus cos squared theta y plus cos squared theta is equals 1. This is coming from the fact that the unit vector has a magnitude of 1. And so if I take the magnitude of this vector, I'll get this. And so this relationship is very useful when you are given one angle, two angles the force make with the axis, and then you are asked to find the other one. You are going to use this formula. So if the forces are known, then we can find the direction as well. So this is what we are saying. The direction cosine cos theta s is Fx over F, cos theta y is Fy over F, and then cos theta z is also Fz over F. And so that is all about the direction cosine and the relationship between the force and its component. Thank you for watching.